Hey everyone. So this is the next lesson in this function ops section, kind of the last section of our big functions unit. Yesterday we talked about sums and differences of functions. And really the big point there was when we want to add or subtract functions from each other, we are adding or subtracting the y values from each other, and the x values are going to stay the same. Okay, so today we're going to look at products and quotients. So instead of adding and subtracting, we're going to multiply and divide. But pretty much all the same things that you learned yesterday are going to apply today. Okay, so when we go to multiply two functions together, we're really multiplying the y values. Or when we go to divide one function by another function, you're really dividing the y values. Okay, so it's going to feel very similar. Products and quotients get a little bit more complicated in the sense of with domain and range, especially with the quotient ones. You often create rational expressions. And so then you need to think through what are my restrictions on x and how does that affect my domain and that sort of stuff. So those are that's something to be careful of. Just like with yesterday too, I said that differences of functions, I couldn't think of the word difference for a sec. I said that differences of functions was a little bit more complicated than sums because the order really mattered. Changing the order would produce a different result. Same thing here. When we multiply things together, the order doesn't actually doesn't matter. So it's probably a little easier, but when we do division, the order does matter. It matters who is the divisor and who's the dividend. So that's just something to be, cautious of. Okay. So last class, we learned how to work with addition and subtraction of functions. Today, we will work with multiplication and division. Just like with addition and subtraction, we will have two notations. So this is often, here's what it's often given to you as f times g of x. I think it's better to write it out as f of x times g of x so that you can see them separately and you kind of know what you're going to do to those equations. Same thing with division. You can write it as f of x over g of x, or sometimes you will see it as f over g of x. And the one stipulation here that you have to remember of, and we were just talking about it, g of x can't be 0. I can't have a denominator of 0. Okay. Given the function f of x equals x minus 3 and g of x is x squared minus 8x plus 15, determine h of x, which would be f times g of x. Okay. Now, when we're doing these guys, we usually write them in factored form because we have a better visual of it. Okay. So x squared minus 8x plus 15, we could factor that. Two numbers that multiply together to give you 15 and add together to give you negative 8 would be negative 3 and negative 5. Okay, so we end up with x minus 3, x minus 5, x minus 3, but then I can put those x minus 3's together. So I have x minus 3 squared times x plus 5. Sorry, x minus 5. Now, all of the stuff we just did with polynomials will kick in. I have an x-intercept at 3 with a multiplicity of 2, which means I'm going to change direction. I have an x-intercept at 5 with a multiplicity of 1, which means I'll go straight through. I have a positive leading coefficient, so my graph needs to end up. This is a degree 3, so it will come into the graph going up and end going out, going up, okay? End going out, going up. I don't know if that was the greatest grammar, but you get what I'm saying. So here is h of x, okay? Now we're going to graph all three functions. So you probably want to pause me, grab your graphing calculator so that you can draw a decent sketch, right? Remember, I've said several times, you don't just want to draw a sketch. I need to have accurate context of your graph. You need to show me numbers. If you're on a grid, you need to have certain numbers plotted properly, okay? Always take your time with these things. Okay, so pause me. And these are the three graphs you should have ended up with. Okay, so the blue graph is f of x, my red graph is g of x, and my green graph is h of x. So now we'll go through the domain and ranges for all three. Starting with the domain, f of x, the domain will be real, g of x, the domain will be real, and h of x, the domain will be real. So they're all real, okay? The range for f of x and h of x, they'll be real because they're odd degrees. But for g of x is an even degree. And so I need to find that maximum point. Sorry, I need to find the minimum point, and a reminder that you can only find that minimum point right now with your graphing calculator, okay? You could deduce that the vertex is halfway between 3 and 5, so you know the x value is 4 and plug 4 in, but it's just as easy to get it from your graphing calculator. So y is a member of the reals for f of x, and then for g of x, y is greater than or equal to -1, and for h of x, y is a member of the reals, okay? All right, now using your graph or the equation, evaluate the following. So we did things like these yesterday. G times f of 0, well, that means g of 0 times f of 0. If I go g of 0 times f of 0, well, g of 0 I don't have here, but I do, right? It's 15. It would just be up here. Even though I didn't show it to you in my window, g of 0 is 15. F of 0 is -3. 15 times -3 is -45. So g times f of 0 is going to be -45. Okay. Okay, h of 2, just let me clear the ink that I had there. H of 2, we can go to here, okay, and we can say, well, h of 2 has to be g of 2 times f of 2. So f of 2, I see right here. Where did my mouse go? There it is. Okay, is -1. And then g of 2 is 3. So -1 times 3 would be -3. I could also, because that's in my window, I could have read it right off of h of x, right? H of x is -3. So the same things that happened yesterday are happening today. Yesterday, the picture showed us that we were adding all the y values together, or we were subtracting all the y values together. Now it's showing us that we're multiplying all the y values together. So whether you take the two original and multiply them together, or you read them off the new graph, it's the same thing. F times g of 5, also known as h of 5. Well, h of 5 is 0. I can read that right off my green graph. Okay. Okay. Same two starting functions, but now we're going to look at f over g of x. So that's f of x over g of x. I would always write it like that first. We already have f of x and g of x in their factored forms from the previous question. Don't have to do anything to f of x, but we factored g of x. And so that's going to be x minus 3 over x minus 3, x minus 5. Now, all the rational characteristics that you know and love now kick in. You want to tell me, okay, I have a point of discontinuity at 3 because I have a factor on the top shared or with the same factor on the bottom. Okay, sorry, I had stumbled there because I was thinking about the next thing I wanted to say in my head, which was, don't make those disappear, right? We've talked about that in rational functions. Keep the x minus 3's there because that's what tells us you have a point of discontinuity, right? Now, when you need the point of discontinuity, though, you need the full point, you need the y value. If those were to be simplified, this would be 1 over x minus 5, but x can't be 3. So if I plugged in 3, I'd have 3 minus 5 on the bottom. Do you want that drawn out here for a sec? I'd have 1 over x minus 5 as my simplified version, right? So if I plugged in 3, I'd have 3 minus 5, which would be -1/2. 3 minus 5 is -2, okay? So my point of discontinuity is at 3, -1/2. I have a vertical asymptote at x equals 5. This is the larger degree is on the bottom. So I have a horizontal asymptote at y equals 0. I don't have an x-intercept because there's no factor on the top by itself. My y-intercept occurs when I plug 0 in for x. So that would give me out -1/5. So 0, -1/5. All these things we know and we can now draw and incorporate into our drawing, okay? So I simplified it there just so that we could have all those conversations we just had. And then these are all the things we just talked about. So now go ahead and draw the two original, and then draw the rational as well on top. I'm assuming you've paused me. And now this is the picture that you should have come up with, okay? And again, we're gonna go through the domain, the range, and for all three graphs. So the domain of f of x and g of x, we already talked about, they were real. The domain of h of x is not real because we have these non-permissible values. So the domain of h of x would be x is a member of the reals, but it can't be those two x values, which would have been 3 and 5. So we'd have to say x is a member of the reals, x cannot equal 3 and 5. For the range, we already know the range of the f of x and g of x, so I'll just put those right back up again. The range for h of x, again, y will be a member of the reals, but it can't be those two things, which is for y, -1/2 and 0. So y can't be -1/2 or 0, okay? Okay, so now evaluate the following, whether you do it from taking f of 0 and dividing by g of 0, or whether you go right to h of 0, it doesn't really matter. H of 0 was the y-intercept for that guy, which we have already discussed was -1/5. Okay, h of 3, well, h of 3 is a point of discontinuity. So we would have to say there exists a point of discontinuity at 3, -1/2. And then f of 4 over g of 4 would be h of 4, which is -1. It's right there. Okay. Okay. New equations. Given the function f of x is 2x squared minus 8 and g of x is x plus 2, determine f times g of x. Again, I probably want to write this in factored form. So if I took the 2 out of there, that would be x squared minus 4, which would then go to x plus 2 and x minus 2. Okay, so we'd have x plus 2, 2 times x plus 2, x minus 2 times x plus 2, which was my g of x. My x plus 2's can come together, so I have 2 times x plus 2 squared times x minus 2. So again, this gives me a degree 3. I have a turning point or a point of tangency at x equals -2. I go straight through at x equals 2. I have a positive leading coefficient. So if we were to graph all of that stuff, which I have shown for you here, you may want to pause me and catch up because I know I just did a bunch of stuff all at the same time there. The domain for all of these guys will be real. I'm going through this part a little quicker because it's very similar to what we just did. The range, again, I need to know the bottom of my my f of x. The bottom of my f of x there is at -8. I can just tell that from the equation, but if you didn't know that from the equation, you could graph it and calculate the minimum point. So y is a member of the reals for g of x. Sorry, this is off. My coloring system is off here because the blue graph is actually my quadratic. Okay, so I do have the right range here, but it doesn't match the color. I've never noticed that before, so I'll change the colors to these later. But so this is for the line x plus 2, and then this guy is for the 2x squared minus 8. Okay, and then the green graph, y is a member of the reals for that guy as well. Okay. Okay, and then figure out the following. So I've got g times f of -2, also known as h of -2, and that's 0. I can see it right there. Okay. H of 1 is somewhere down here. So I could plug 1 into my h equation. I could plug 1 into f and g and then multiply them together. It doesn't matter, you're going to get the same answer. So it's all a matter of what's the easiest thing to do. So I figured out that Plugging 1 into the two original equations were going to give me -6 and 3. So then I knew that h of 1 had to be -18. Okay. And then f times g of 4, also known as h of 4, I could plug 4 in here, or I could do it the same way I just did it. I just plugged it directly into the h of x equation this time, just trying to show you all the different ways we can do this and still get the same answer. Okay, so then that ended up being 144. Not on our graph, but we know just mathematically that it ends up being 144. Okay, now we're going to do the division. So we would end up with x plus 2x minus 2 and 2 on top, and x plus 2 on the bottom. So again, what does this give us? Well, it gives me a point of discontinuity at -2. I will show you the simplified version here. Oh, no, I won't. Look at that. So it gives me a point of discontinuity at -2, and that would leave me with 2 times x minus 2. But I know that x can't be -2 there, so if I plug -2 in, that would get me -4 times 2, so that would give me -8. So the point of discontinuity is at -2, -8. I have an x-intercept at 2, 0 because I have a factor on the top by itself. I have a degree on the top higher than the degree on the bottom, which means there's no horizontal asymptote here. What else do we need to talk about there? I think that's everything. Okay, so now go ahead and graph them all. Your graph should look like this. Okay, so h of x ends up becoming a line with that point of discontinuity. So real and real for the first two. But now for the h of x, it'll be real but can't be -2. And then again, for this guy, I have these mixed up again, so I have to switch them. This guy is for the g of x, so he should be red. The f of x will be greater than -8, so that should actually be blue if I wanted to color code this properly. And then for the green graph, it's real, but it can't be that y value at the point of discontinuity, which was -8. Okay, so y is a member of the reals, but it can't be -8. Okay, awesome. So now it says using your graph or equation, evaluate the following. So f over g of -2, that's the same as saying f of -2 over g of -2. Okay, also known as h of -2. When I look at h of -2, we can see that that's where that point of discontinuity is. So it does not exist. There's a point of discontinuity at -2, -8. h of 2, I can read right off the graph is 0. f of 0 over g of 0. Well, I'm going to use the h equation this time, plug in 0 and solve, and I get -4. I could have also just gone right here and seen the -4. I could have also gone and found what f of 0 was and found what g of 0 is and divided. Okay, that would have given me -8 divided by 2. So it totally doesn't matter either way. Okay, if f of x is x minus 1 and g of x is x squared minus 1 and h of x is root of x plus 2, determine each combined function and state any restrictions. So if I multiply them all together, I just multiply them all together. But now these two x minus 1s can come together. So that'll be x minus 1 squared times x plus 1 times the root of x plus 2. I'm not asking you to multiply this out. You would leave it in factored form. And the restrictions come from the radical in this one. So this has to be positive. So x has to be greater than -2. Okay, and that actually becomes a domain as well. Remember, the restrictions on a radical create the domain of the graph. Okay, so x has to be greater than or equal to -2. I didn't write it as domain because it didn't ask me for domain. It just said the restrictions. Okay. Okay, now we're going to try g of x times h of x over f of x. So again, we're just plug in everything you know. Okay, so this is what I'm looking at. Then I have restrictions that x can't be -1, or sorry, x can't be +1 here, and x has to be greater than -2 here. Now, once you list all those restrictions, you have to ask yourself, do I need to say both of those, or does one encompass the other? In this one, you do need both of them because x has to be greater than -2 would include x being 1, and so you still have to say, oh, okay, so it can be greater than -2, but it can't be 1. If one of them kind of trumped out the other guy, then you don't say them both, okay? But for this guy, you do need to say them both, because that 1 would be in here allowed, and it's not allowed, so we have to also state it. I guess that's hopefully a clearer way of saying that. Okay, given the graphs of f of x and g of x below, determine the value of f over g of 0 and g over f of -4. Okay, so f over g of 0, so let's go to 0, and that would be 4 over 0. Okay, so that would create a vertical asymptote. It would not exist. There is no value for f over g of 0. And then g over f of -4 would also create a vertical asymptote, because I would have, what's that, 8 over 0. So I'd have 2 vertical asymptotes there. Now, how do I know? Sorry, I'm getting ahead of myself. Let's just answer that question first. So f over g of 0 is undefined, and g over f of -4 is also undefined, okay? All right, then it says, explain what is occurring. What would be occurring here is a vertical asymptote. Now, how do I know, which is what I was about to ask, whether I have a vertical asymptote or a point of discontinuity? In order to be a point of discontinuity, the factors have to be the same, right? So the factor on the top and the factor on the bottom have to be shared, okay? The factor on the top here ended up being working out to be 8, right? And the factor on the bottom was -4. So because they're not in the same spot, it doesn't work as a point of discontinuity. It would have to be a vertical asymptote, okay? All right, state the domain. Now, we've talked about this yesterday. We talked about the fact that you have to look at the restrictions overall. The new graph can't exist unless both of the original graphs existed. So although you know this is a computer drawn graph, you know that the g of x is going to go on forever, f of x has a distinct starting point at -5. And so the new graph can only start at -5. Even though g continues to -infinity, it won't work in h because both graphs have to exist. So we would say that the domain of h of x has to be greater than -5. And then I also had to state in here that x can't be -4 or 0 because the domain won't exist, or x won't exist at those points because they had horizontal asymptotes. Okay, so that's a great little test question because you don't have that picture in front of you. You're not just reading the domain off the picture. You are actually figuring it out from what you know of the original graphs. So I know we talked about this yesterday. You had a very similar kind of comment at the end of yesterday's lesson, but it's worth reviewing the point again. When performing operations on functions like multiplying or dividing, the only value that will change is that dependent variable, or the y variable, the y value. Never touch the independent variable, the x value. The x values always remain the same. The y values are the ones that you're multiplying or dividing or you're adding or you're subtracting. Here is what you're doing now, okay? Hopefully this is feeling good, but if it's not, make sure you come and chat with me and let me help you clarify anything that needs to be clarified, okay? In the meantime, I'll leave you be to work and you will see each other for a composition of functions, okay? Take care, guys.